we're going to look at the basics of functions. We're going to start with some vocabulary first, and our first one is a relation, and that's a mapping or a pairing of input and output values. Now, this pairing could be a list of ordered pairs, so 2, 3, 5, 7, 8, 1. It could be written as a table of values, so I could do an XY chart, and I could put my X values here and then their partners next to them. It could be written as a sideways table of values where I would do my X and Y and then partner up that way. The mapping part, when they say mapping, most of the time they're referring to just a different type of a diagram. So I would put my input values on the left here, my 2, my 5, and my 8. And on the right I would put my 3, my 7, and my 1. And then I would draw arrows to those. So that's telling me that 2 is partnered with 3. So that's what a mapping could look like. These could be in boxes, they could be in just about anything. But notice all of these are telling you the exact same information. 2 is paired with 3. 2 is paired with 3. 2 is paired with 3. So a relation is just any sort of pairing. Now, when we have a relation, we have our domain, and our domain are the input values. Most of the time when we are dealing with this, we are talking about XY pairs, and our domain would be our X values. It could also be called our independent variable. So all 4 of these words have the exact same meaning. In our example up here, our domain would be 2, 5, and an 8, because those are our input values. Now, to go with that, we have our range. Well, range are the output values. And most of the time that would be our Y values. And it could also be called our dependent variable, or dependent values. So all 4 of these indicate that we're talking about range. Now, you've probably done some work with a coordinate plane, and on our coordinate plane we have 2 number lines that intersect. The vertical number line is our y-axis. The horizontal number line is our x-axis, and the place where they meet right here is called the origin. That would represent 0, 0, so that would be 0 x's and 0 y's. And then when we put on our x and y axis, it divides our coordinate plane into quadrants. And the quadrants start in the top left corner with quadrant 1, and then they go counterclockwise. So quadrant 2 is in the top left corner, quadrant 3 bottom left, and quadrant 4 is in the bottom right corner. Okay, and our next one. Now this definition is probably a new one, a function. A function is a relation, so we know we're going to have pairing of numbers because it's a relation, but it's a relation in which each input has only one output value. So each x can only be partnered with one output. So if I make up a relation, I'm going to do it as an XY chart. I'm going to have a 3 with a 5, 2 with a 4, 1 with a 7. Now, as I look at this, I have to decide, is it a function? And to be a function, each input has only one output. So I have to look at my 3. And as I look over here, I see that it only has one output value. My 2 only has one output value. My 1 only has one output value. So the way this is written right now, I have a function. What I'm going to do is I'm going to go ahead and plot all of these points. I'm going to graph these over here on my coordinate plane. Okay, I have them all plotted, and we already decided it's a function. Well, what I'm going to do is I'm going to show you what would we have to do to make it not be a function. So I'm going to pick one of my x values, one of my input values. I'm going to pick 2. And I'm going to match it up with something other than 4. So I'm going to match it up with 2. Now it has become just a relation. It's no longer a function because right here I have an x value that has 2 different partners. That is not allowed. It says the input values have only one output value. Now if we go over here and look at the graph of this, notice the position of these 2 points, which are the ones that are causing it to not be a function. The 3, 5 doesn't cause a problems with anybody else, and the 1, 7 doesn't. So look at these 2 and notice their position. I'm going to change it a little bit. I'm going to take off that 2, 2 that I just added. So keep in mind the visual of their position. And I'm going to add a different point. This time we're going to have the 3, 5 be causing the problem. So in order to make that a problem, I'm going to put it with a 3, 2. So when I go over here and graph 3, 2, now the ones that are causing the problems are the 3, 2 and the 3, 5 right there. Notice their position with respect to each other. One thing that we can do to check to see if we have a function is we can do what's called the vertical line test. And the idea behind the vertical line test has to do with these two's position. Now, in this case, the 3, 5 and the 3, 2 cause this to not be a function. Well, if you look at a vertical line, that would pass through both of those points at the exact same time. So our vertical line test tells us that if we can visualize a vertical line passing through our graph, and if it does not touch any 2 points at the same time, then it's a function. If it does touch more than 1 point, like right here, a vertical line would touch those 2 at the same time. If it does touch more than 1 point at the same time, then it's not a function. So that's a quick way. If they give you the graph, you can look at it and pass a vertical line across it and tell if it's a function or not. Okay, let's go back to our original now. So I've turned it back into a function. I got rid of those ones that were causing a problem. And this time I'm going to put up a number. I'm going to put up 4, 4 here. Because notice now I've got those two matching. So if I go over here and plot 4, 4, I have my point right there. But what you have to understand is that this is still a function because our rule says that each input can have only one output. It doesn't say how many outputs our inputs can have. So just because I have a 4 here and a 4 here, since there are output values, that doesn't cause a problem with it being a function. It's only the input values. And if you look back over here at the graph, when I plot that one on here, my vertical line test still passes. A vertical line would not touch more than 1 point in any spot. So this would still be a function because doubling up on your output values isn't a problem. It's only the input values that we have to worry about. Okay, now we're going to look at this idea called function notation. And this is what function notation normally looks like. And it's read f of x. And what it does is it indicates that we have a function called f that is written in terms of the variable x. We can also have things that look like this. This is still function notation. It would be read g of x. And it's indicating to us the exact same thing. It's saying we have a function, this time it's named g though, and its variable is going to be x again. Now the reason we have these different functions, why it's not always f, is because if I'm looking at two functions at the same time, if they were both f, I wouldn't know which function I needed to be working with at any particular time. So we're going to look at a problem here. This problem right here would be read f of 5. And if you look at what it normally is, normally it's f of x. Well, my f stayed the same, but my x was replaced by a 5. That's telling you that you need to go into your formula and you need to replace that x with a 5. So instead of having that x in my equation, I'm now going to put 5 in it. Then I can go ahead and calculate it. So f of 5 is equal to 20. So this is a way of saying, here's my function. I want you to solve the function when x is equal to 5. Now we can do that for g also. This time, since it's g, I know I need to be using this equation over here because this is my f function, that's my g function. So g of 3 is telling me I need to take this function here and I need to take that x out and put a 3 in it. So I would have 4, and then instead of that x, I put a 3 in, solve that one out, and I get 5. G of 3 is equal to 5. So this is telling me that my function g, when I evaluate it for x equals 3, I'm going to get back a 5. Now if you look at these equations, you might be thinking, well, normally it's y equals 4x minus 7, or y equals 3x plus 5. g of x or f of x is really saying the same thing as y. It's saying, what's my output value? Well, my y is my output value. So it's just a different way of writing y. It's called function notation. You will see this used all the time in your upper level math classes. Okay, now so we've talked a little bit about functions, and now we're going to look at graphs. When we have an equation in two variables, and when they say it's an equation in two variables, that means we have like an x and a y. We have two variables that make up our equation. We can often represent this by a graph, or we often need to represent this by a graph. But one thing that you have to really understand is that a graph is a visual representation of an equation. It's the picture of whatever our formula is. But here's the important part. It represents all the solutions, the xy pairs, of that equation. Which means if I were to have a graph, this point, whether it be the point 5, -3, that would have to make my equation true for whatever this line is that I graphed. Any point on this line has to make my equation true. That's really what a graph is. It's all the solutions of an equation. So we're going to look at how are we going to do this graphing. Now, one thing that you can always do if you're not sure how to use any formulas or things like that to draw these graphs like parent functions and things, you can always create a table of values until you see a pattern. Some things to keep in mind though, when you do your table of values, make sure you pick some positives, pick some negatives, pick some zeros. Probably a good idea to pick some fractions when you get into some of the more complex ones. So we are going to graph f of x is equal to x squared minus 4. Now remember, this is just like saying y equals x squared minus 4. So I'm going to do my table of values. I'm going to do my inputs and my outputs, my domain, my range. I'm going to start by picking a couple of negative numbers. So I'm going to put -2 in here, -1, 0, and then 1 and 2. So I've got some negatives, I've got 0, and I've got 1 and 2. Now in order to figure out my output values, I have to substitute each one of these in. So I'm actually going to plug -2 in here. Well, -2 squared is a positive 4. 4 minus 4 is 0. So when I put -2 in here, f of -2, I get back my output of 0. I'm going to do the same thing with -1. So I'm going to put -1 squared in there, which would be 1 minus 4. I'm going to get back a -3. Going to plug 0 in there. 0 squared minus 4 is a -4. 1 squared minus 4 gives me a -3. And then 2 squared minus 4 gives me back a 0. Now I can take these points from my table of values and I can plot them over here on my graph. Now that I have them plotted on my graph, I can see the pattern that's happening. We've got a parabola here. So then I can sketch my actual graph in there. So now if I actually think about what the meaning of a graph is, each one of these points on my line would represent a solution of that equation. So I could pick anything on this line and plug it in here and it would make it true because that's what a graph is. It's all the solutions.